computer. I was assuming people would join via Zoom. So first off, if you feel symptoms in general, or you're sick with anything, stay home, stay away from me. I like you, but not that much. So, seriously, just stay home if you're feeling unwell, even if it's not COVID related. So cold, cold symptoms, even just stay home. Listen, and what you'll do, all you have to do is just shoot me an email. One of two things. Either, you shoot me an email which says one of two things. Hi, I'm sick, I'm not coming to class. Awesome. Or hi, I'm sick, I'm not coming into class, but could you start the Zoom for me? In the first case, just watch the lecture recording afterwards, which has been my practice for classes since I started teaching here in 2016. So just watch the lecture recording if you have to. If you've got something that's going to that knocks you out for a couple days, that's part of the reason I have the lecture video flipped, by the way. I started thinking about this even more so when we had the mumps outbreak back in 2019. So, because there were, and it just bothers me. It just irks me to no end that I wrote a small presentation on why you should record your lectures to a conference, and that got rejected in 2019 and in 2020. I feel like I need to resubmit that with no changes other than I originally submitted this in 2019. Who's laughing now? So, but my pettiness need not be part of the class. So I've created, so here, fittingly, there's no better week to do an awkward transition than this week, fortunately for us, which is the Big O module. Now this homework is, now you should have had or will be having some light introduction to the mathematical, wait a second. Why is that there? That's unnecessary. Overview is blank. Really shouldn't need it. Okay, Big O videos, that's what it is there. So your Big O videos, right? You probably had some exposure in a previous class. Raise your hand if you had some exposure to Big O notation in previous classes. Okay, what class was that? Discrete 2. Anyone else? Yeah. Right. Okay, so you'll have had some, we still are trying to figure out the best way to introduce this, but also because the requirements of some classes, you may not have had an introduction to it, and that's fine. But I should tell you the perspective that we're coming from is not the perspective of discrete math. Discrete math is all about proving and theorems, and eventually I might have the textbook and some videos on that. But for right now, what we're going for is more of a more practical view, which is what does it feel like? What can we, not mathematically, what can we prove as mathematicians, as theoretical mathematicians, but more, what can we observe like scientists? Like, if I do this, what if I change the input this way, what do I observe as the output? Does that make sense? Right? And so the main thing what we should look at, given an input size, if we change that by a factor of 10, what do we see? Right? And right now we're looking at 3, and we'll eventually change that to a factor of 2, but for right now it's easier to think of in 10. So and right now we're learning about 3, or we're going to be working with 3 different classes of algorithms: constant time algorithms, linear time algorithms, and quadratic algorithms. If we're dealing with a constant time algorithm, it doesn't matter how big it is. It's always going to take the same amount of time. So that would be something like the size function, okay? The size function in a Big O, so the size, it's just going to return the size of it. It doesn't matter how big it is. It's being stored in a variable. We're just retrieving a variable. The get operation is something that's is also constant time, because we're just going to a location and grabbing an item from there. The way the array based, because array lists use arrays underneath, there's just like this very easy to use kind of equation, which basically does works off an offset. Second. Share screen, whiteboard. And what we'll do over here yes. So basically, if I have some kind of array, we've done it like this. If I have some kind of array, right, 0, 1, 2, 3, 4, right, this array starts at some memory address. Let's call it 0x A, B, C, 0, okay? That's like the memory address at the start of the array. So the way we find an address or we get anything from an array is as follows. You take the index of the start. So the index of the start, and then you add in some kind of the index that you want times and this isn't, you don't need to know this for an exam. I'm just trying to clarify. The index times a certain amount of size of element, which in most cases is a 32-bit reference. So basically, we take the start and then we take the index of what we want multiplied by how many bits the size of one of these things are, which is typically 32 bits, right? So this guy would, if this guy's ABC 0, and each of these is a byte, one, or increasing this by 1 means move 1 byte over, then this guy would be 0, ABC 0, this would be ABC 0, sorry, ABC 4 for this guy, and this would be ABC 8, and this would be ABC 12, and what is 12 in hexadecimal? So 10 is A, B, C. So ABCC, right? And that kind of computation is weird for us, but it takes the computer basically constant time because it's just a mathematical operation. That is how array lists are able to get objects, okay? So now a linear time algorithm, that's basically adding to the front. Basically, we would have to shift all the items over, and that we have n items and we're each shifting them by 1, so it takes O of n time. An O of n squared, now an O of n squared operation, that's when we have to basically, that's something like the isUnique function that you wrote, okay? The first array list operation, where we've given an array, it's going to take, basically we have to compare each item to each other item. So each of the n items does n comparisons, okay? Make sense? So a good example of that is an O of n algorithm is if I have to grade every exam. If I've got 40 students in a class, it's going to take me about the time to grade one exam times 40, right? About that amount of time. But if I'm like if I'm being like super rigorous about checking for plagiarism and identical answers, right? It would take me the amount of time to check one, basically I'd have to check, it would take me the amount of time I would have to compare to everybody else. So every question compared to every other question. Now add one more student. The amount of time it takes me to grade an exam doesn't take me much more time than grading one more exam, right? It's one more exam. I've gone from 40 to 41. But now, if I'm doing that really rigorous plagiarism check, I'm comparing that exam to 40 other exams. So I've just added 40 more checks, right? That's a quadratic time algorithm. With quadratic, adding one more thing basically means I have to do n more time. Or to put it another way, quadratic time algorithm, if I increase the amount of size I have by a factor of 10, if it's a linear time algorithm, got 10 times more work. If it's a quadratic times algorithm, I got 100 times more work to do. Okay, those are the three kind of growth rates we're looking at: constant, linear, quadratic. Later on in the semester, we will be dealing with logarithmic time and n log n. And logarithmic time, that sounds scary because we don't understand how logs work. Our puny 8 brains just don't get it. That's fine. That's because you've been, the mathematicians, they focus on that weird relationship, the two formulas, how basically logs and exponents are related with their bases and stuff, and the value of the exponents. That's a load of baloney. I mean, it's true, but it's so unhelpful. Logarithms, as we'll learn, are basically, they are telling us the amount of times we can split things. That's the way we'll be viewing it, and I'll get into more detail about that. So the homework for this week is actually going to be a really weird math worksheet. Now, I don't believe, because I have enough students, I can say I don't like the way that most math exercises are done. I don't like the way most math exercises are done. Okay. Which is, we've got this sheet. It says 5016 on it because I last revised it for my graduate course. Okay, here I want you to basically use the first steps over here to try to figure out what the O of n times are. Just learning the language of O of n. T of n means the amount of time an algorithm takes. Big O is basically putting a kind of magnitude on it. Big O says it's never going to be worse than this factor. And O of n and cubed growth rate, or O of n growth rate, or whatever. Okay, the 3 and 4 are trick questions, just FYI. If you've taken Calc 2 and done your infinite series or and their convergences, you may recognize them. If you've not, try Googling 1 plus 2, try Googling the series, okay? Now, but what I was saying is that about this being a different than most math things is that you're going to be demoing this. And because you're going to be demoing it, I'll go through and I'll say, this is right, all these are right, except for this one's wrong. And I'll tell you to fix that one. And when you fix it, you can get your full credit. Okay, that's what I mean. So there's no reason not to get full credit. Just, okay, you'll be answering some questions about these. I've got a puzzle that's on the last page from a book that I like. Although my wording for it is kind of terrible and ambiguous for number 18. So there's a lot of proper ways to interpret that, but that's fine. It's the thinking that I care about. On this 5th page, you'll be looking at an algorithm called BOGO sort. BOGO sort is an algorithm that just does not exist outside of academia. It specifically exists for the purposes of classes like these, because it's a terrible sorting algorithm. The algorithm is as follows. I want to take a deck of cards and shuffle it. The way I shuffle it is by throwing it up in the air, picking up all the cards, and seeing if it's sorted. Okay, that's the algorithm, which is that I just simply randomly shuffle it until it's sorted. How long? And so the question is, how long does that take? Okay, there's one other sorting algorithm that is similar. We call that Stooge sort, but that's reserved for more of the algorithms course. Okay. So, yes. So yeah. And then finally, and most importantly for this, most importantly for this, last 20 points for each of the methods you wrote in lab 2. I want you to figure out the time complexity of each of those methods you wrote. Okay. So you can go ahead and start on it if you haven't finished lab 2 yet, but to finish it, you'll have to have finished lab 2. Make sense? All right, so with that, we'll go ahead and I'll stop talking and I can let you get to work.